So in this session, we are going to study a couple of things. One is the connection between correlation and the convolution. So because we have already studied how to do convolution analytically. So once we find the relationship between correlation and convolution, we will also be able to find out correlation analytically. That is the reason for studying this first thing. And the second thing we'll study is the autocorrelation, which simply means that you are finding the correlation of the signal with itself. And that is an important operation, as we shall see later on in some of the applications. So these are the couple of things we are going to study. The first one is brief. Let us start with that. So what are we studying? Analytic solution to continuous time cross correlation. Okay. So this is how we had defined the cross correlation: Rxy tau xt into yt minus tau and integrated with respect to time. Now this can be related to convolution, and let us see how that comes about. Now suppose xt is given to us, so what we can do is we can simply change the variable from t to tau. So from xt we get x tau, and yt is also given to us, so again we change t to tau, so we'll get y tau, and then fold it, time invert it, so you get y of minus tau. Once you have done this, then what you do is you perform convolution operation on x tau and y of minus tau. So from the definition of the convolution, we can write it like this: minus infinity to plus infinity xt y of minus, because of this minus sign, tau minus t dt. Note that in this definition of convolution, this looks a little different, mainly because the roles of t and tau are interchanged. In this case, when you are integrating with respect to t and put the limits, what you will get will be functions of tau. Okay. Now if you open this bracket, what you will get will be t minus tau, because minus minus t will become t, and this is minus tau. So this is xt y of t minus tau. But what is this right hand side? It is equal to the cross correlation between x and y. That is this xt yt minus tau, same as this. So what did we do? We started by defining the convolution operation between x tau and y of minus tau, and we have shown that it is same as rxy tau. So the point is, if you want to find the cross correlation analytically for a continuous time signal, then what you do is simply change the variable first and then perform this convolution operation. So since we have devoted enough time for seeing how to analytically calculate the convolution, we will not go into this. You can easily do this. So that is how you can obtain correlation analytically through the operation of convolution. Alright, so that was the first topic that we wanted to study. Next, what we want to study is the autocorrelation of an energy signal. So we'll first consider a discrete signal, and later on we will see how to tackle the continuous time signal. So for a discrete signal, the autocorrelation is basically, the definition is similar to the cross correlation, except that your second signal is now same as the first signal. So you are finding the correlation of the signal with itself. Now this may sound a little funny, but as we shall see, this autocorrelation operation is quite useful in many applications. Alright. So we will be able to show that this autocorrelation is maximum at zero delay. See what we are doing in this case, we take xn and then we take delayed version of xn. And how much delay? Since it's a discrete signal, it is in terms of number of samples. If m is equal to 0, there is no delay at all. If m is equal to 1, it means delayed by 1 sample. M equal to 2 will mean delayed by 2 samples. And if this is n plus m, so if m is equal to 1, then it will be advanced, and so on. Now what we are stating here is that autocorrelation is maximum at 0 delay, that is m equal to 0. So best way of why this comes about is to look at an example and work it out. So let us take one discrete signal. Let's say xn is equal to 1, minus 2, 3, minus 4. And we want to find the autocorrelation of xn. That means we want to find the correlation of xn with xn itself. And this we want to do this for various delays. So first what we do, we advance this xn sufficiently so that there is just an overlap here. So only one value is overlapping. No point in taking xn plus 4 because then the two will not overlap at all and you will not get any correlation value. So if you consider the advanced version of xn by 3 samples, then it is shifted to the left by 3 samples and 1 and minus 4 are aligned. So when you calculate the sum of the products, so 1 into minus 4, that is equal to minus 4. Now this is the maximum advance that you can do. So now what you can do is you can start delaying. So you delay it once to the right, which means that the net advance is by 2 samples starting from xn. So when we advance it 2 samples to the right, 1 and 3 are aligned, minus 2 and minus 4 are aligned. So 3 into 1 is 3, 4 into 2, minus 4 into minus 2 is plus 8, so you get 11 here. You advance it further, you get 3 alignments now, so 1 and minus 2 and 3, 3 and minus 4. So if you calculate this, you will get minus 20. Finally, when my m is equal to 0, that is 0 delay, in that case you will find that there is complete alignment of both the values, both sequences, 1, minus 2, 3, minus 4 is 1, minus 2, 3 and minus 4. Now it's easy to see why you get maximum value. There are two things here. One is that you have got maximum alignment, all are matching here. So you get 4 terms which are the product terms. Second is, no matter whether the sample value is negative or positive, the product is always going to be positive because minus into minus is going to be positive, and of course plus into plus is definitely going to be positive. So these two factors, that the two signals are aligned completely when there is 0 delay, and also the fact that every product term will be positive, will give rise to the value of the autocorrelation which is maximum for 0 delay. So in one case you got various values, minus 4, 11, minus 20 and 30. Now let us see how to do this calculation through a program. So this is as usual clear console, clear figure. This is our X. Now we calculate the autocorrelation again by using the XCOR function itself. So the function is not changed, but what changes is the parameters which are passed. So X is one sequence and the second sequence is also X itself. In case where your two sequences are different, you get cross correlation. When both the sequences are same, you get autocorrelation. So you still use this, and what you get here, you get the value of this autocorrelation in the variable y, and in the variable I you will get the delay for this particular value. So then you can plot this. So stem, IY, line width. So these are the standard things we do, and then when we plot it, this is what we get. So this is for delay 1, delay 2, delay 3, and if you compare all these values, you will find that delay 0 you get maximum value which is plus 30. So this is an important property of the autocorrelation. For 0 delay, the autocorrelation is going to be maximum, and this is a property which is quite useful in signal processing. We shall see that when we study some applications. All right. Now let me demonstrate to you another program. In this case, what we are going to do is to simulate a continuous time sine wave. And what is it that we want to accomplish through this program? So let me explain. We write the program to study the following. First of all, calculate and plot the sine wave. We have done that before and we'll do it again here. Then calculate and plot the noise. Then what you do, you calculate and plot cross correlation between a sine wave and noise, and also plot autocorrelation of the sine wave with itself. So autocorrelation for zero delay of course will be maximum. Now when you try to find the cross correlation between a sine wave and the noise, you can imagine that you will not get a very large value. The reason is noise is a random variable, so it varies in a very haphazard fashion. Sine wave is of course a systematic waveform. So when you perform the cross correlation, what is cross correlation? It shows similarity between the two signals. Now one is a sine wave and other is a noise, so certainly there is no similarity between the two. So you expect that cross correlation between a sine wave and the noise is going to be small compared with the autocorrelation of the sine wave with itself. So this is what we want to demonstrate through this program. And in case you are wondering why it is important to show this, later on in our next session, we'll study one application of this principle in radar system. So then you will appreciate why the study of these things is useful. Okay, so let us look at the program now. So clear CLC, CLF, F equal to 100. So what we are doing is we are plotting a sine wave whose frequency is 100 Hertz. And since we are generating a continuous time signal, our sampling frequency should be much larger than this frequency. So we are taking it 100 times this. So that is 10,000. 100 times 100. So that is my sampling frequency. So the sampling time is the reciprocal of the sampling frequency. So it is 1 by Fs. Then T is the time period of the sine wave itself, and it is reciprocal of the frequency, that is 1 by F. Why this T we calculate? Because we want to plot certain number of cycles of the sine wave in order to see the sine wave clearly. So then how many cycles we want to plot? So that is stored in the variable called as capital N, that is equal to 10. So when we generate our sine wave using an appropriate time vector, we will be generating 10 cycles of the sine wave. Okay, so we now generate the time vector. So t equal to 0 ts n into t, because t is the time period of one cycle, multiply by n. So this will correspond to the time corresponding to the 10 cycles of the sine wave. Okay. Now generate our sine wave as usual, sine of 2 pi ft. So this will vary between -1 and +1 as usual. Every sine wave has that property. Then we want to generate the random signal. So what do we do? Now we want to generate the random signal whose samples in number are same as the number of samples in x. So what we do is we calculate this n1 equal to length of x. And using this, we generate our random signal. So y is equal to -1 plus 2 random 1 comma n1. Remember that this random signal generates values between 0 and 1. So when this is 0, the y will have a value which is -1. And when this is 1, this is 2 minus 1, it will 1. So just as the sine wave is changing from -1 to +1, the noise signal is also changing from -1 to +1, except that the waveforms have quite different shapes. This is quite haphazard, quite random, and this is quite systematic. Okay. Then what you do? Then you want to find the correlation between the sine wave and the noise. So x is our sine wave, y is our noise. So we use x core, and the correlation is stored in C, and the delay is stored in the variable called as lags. Okay. Then we also want to find the autocorrelation of the sine with itself, that is stored in x. So we execute x core x comma x itself and store the result in D. This is the autocorrelation, and the delay is stored in lags 2. So we have got everything available now. So we would like to plot x, we would like to plot y. So that plot will tell you how the sine wave looks like. This plot will tell you how the noise looks like. And finally, in the third plot, what we are going to do is to plot the autocorrelation of the sine wave, and on the same graph we will superimpose the cross correlation of the sine wave with the noise. Idea is to show to you that the autocorrelation will have a much larger value compared to the cross correlation of the sine wave with the noise. All right. So rest of it is just plotting the graph. So I'm sure I don't have to explain this. So you first plot the sine wave, then you plot the noise. Okay, that is Ty. Remember, y was your noise. This is your noise. And then what you do, then you plot the first plot the cross correlation. C, remember, is the cross correlation. And then you also plot the autocorrelation. Remember, D is your autocorrelation, X with X itself. And when the reason for plotting this on the same graph is that it's very easy to see that the cross correlation with the noise is much smaller than the autocorrelation of the sine wave with itself. So let's look at the plot. This is our sine wave. So we have plotted 10 cycles. So since the frequency was 100, this entire time period is 0.1 second. And using this, we generate noise. As you can see, the two wave shapes are not at all similar to each other. They are therefore not at all related to each other. And then in the third graph, we plot the autocorrelation, which is the red waveform here, and the blue waveform, which is the cross correlation. So as you can easily see, the cross correlation with the noise is much small compared with the value of the autocorrelation of the sine with itself. And you can see that at t equal to 0, this autocorrelation is maximum. All right. So in our next session, we shall see how to make use of this in order to use it in radar systems. But for now, that's all.